Okay, cool. So, all right, jumping into it. Here's just a review question. So elements form compounds because they want blank. So A, to get 8 electrons. It should be 8 valence electrons. That's a good start. Noble gas configuration. Yes, they want the noble gas electron configuration. That's how they're happy. So let's say fluorine, for example, in 7A, wants to gain 1 valence electron to get to this noble gas configuration. Then we didn't really learn about, or we did learn about, this is electron configuration. So they want the NS2, N meaning an integer, P6. And that's exactly what they want. This is just another way of saying electron configuration. If I wrote 2s2, 2p6, you would understand, oh, that's on the second row, and then it's the noble gas, it's neon. So yeah. So they all want to achieve the noble gas configuration, whether this is n equals 1, 2, well, not can't be 1, n equals 2, 3, 4, etc. So all the above is the answer. So that's what they want to be happy. So types of bonds. We talked about 2 of these in detail. So you know there's ionic and covalent, and then there's metal-to-metal bonds, which are metallic bonds. So in metallic bonds, instead of the electrons being transferred like ionic or shared like covalent, they're actually pooled together throughout, and they're kind of shared equally or just pooled in the atoms. So you have a sea of atoms, and they're all metals, and you know how metals, how easily they like to lose electrons, right, from ionic bonds. But the same thing applies. But if you have all metals, the electrons are just going to be jumping all over the place, and they don't really have a place to call home. That is why metals are very good conductors of electricity, because all electricity is current, right? So it's current, and what is current? Current is movement of electrons. So metals are the easiest elements, they have the easiest time in moving electrons. So that's why they're very conductive. So we already know this. This is just how to determine valence electrons in an atom. We know 1A, 2A, 3A, all the way to 8A. We understand that. So we're gonna cover the basics of Lewis. I don't like the way they break this up, but Lewis structure is the 3-dimensional orientation, or it can represent the 3-dimensional orientation of covalently bonded compounds. Now, we're going to learn about this more after we learn about lattice energy, but basically we're going to follow different rules. One of them is the octet rule, which basically means that there has to be 8 valence electrons around, well, most of the atoms, but because not everyone follows the octet rule, but a lot of them do, such as oxygen and nitrogen, where there has to be 8 valence electrons either in the form of bonded electrons or non-bonded electrons that partake in the covalent compound. So, and then, like I just said, several elements violate the octet rule. We'll talk about that more in detail later on in the lecture. So we're not really going to cover Lewis structure for ions, because I think that's stupid, because an ionic bond, so just to get this straight, ionic bonds don't have shapes. It's kind of like if you took 2 bowling balls and stuck them together, they're just going to roll around, like, and you like kind of force them together with force, right? They're not really going to create a shape. It'll always be just like 2. It'll always be just like 2. Like, no matter how you orient it, it'll always be, I'm drawing now on here. No, that's a square. There we go. It'll always be like this, no matter how you orient them. So it can go around like this, but either way, even if you have 2 ions, even if you have 3 ions, so let's say it's magnesium chloride. Let's say this is Mg, and these are Cl, and then Cl, because you know magnesium chloride is MgCl2. So no matter how you orient this, they're going to be just revolving around each other like that. They're just going to be around. And the shape is not really important because it changes all the time. The shape of ionic compounds it's not held together by the positioning of the electrons. We'll put it that way. So it's always revolving and moving around the central atom. But it's not going to be like this. It's always going to be, you know, because the magnesium is positive 2, and each of the chlorines is -1. So there is no defined shape for ionic bonds. That's why Lewis structures is kind of dumb, but the way they represent it is still important to look at, because basically these dots, if you haven't caught on already, represent the valence electrons in the atom. So for fluorine, you have 7 valence electrons, so you have 2, 2, 2, and 1. And then once it becomes an ion, meaning it takes the valence electron from lithium, it'll become fluorine with 8 valence electrons and a total charge of -1. So here's how they're going to look like. That's what this slide is mainly for, just for you to understand how the Lewis structured atoms are going to look like with the dots. So each dot represents an electron, and each line represents a bond, but we didn't really see the bonds yet. So here's another example of an ionic bond using the Lewis structure principle, where you take one electron from each lithium, they give it to the oxygen, which has 6 valence electrons. It needs 2 to have a satisfied octet rule, and you get oxygen with 8 valence electrons, or a noble gas configuration that has a charge of -2. So we understand this already, but that's just, it's going to be more relevant, and you're going to learn more once we do it with covalent bonds. All right, so any questions so far? Okay, so far basically. Okay, so lattice energy. So let's say you have a brick of NaCl, right? It's a repeating pattern of NAs and Cls, and each substance has its own unique repeating pattern structure, and this structure is called the crystal lattice. So Na and Cl, it might have some arrangement that maximizes the interaction between the plus and minus ion, between the Na cation and the Cl anion. But other substances like silver sulfide, for example, has a different lattice structure because it has different charges. Each of the atoms have different sizes, which we learned about last class about atomic radii. So the spatial arrangement of the lattice will be different. So it's important to know that every ionic substance has a slightly different lattice structure. That gives them a different lattice energy, because the lattice is and so here's the lattice. You have your pluses and minuses over here in the whole lattice, but the energy associated within one particle of the lattice energy, one molecule, let's say NaCl, right? The energy is proportional to their charges divided by the distance. So if you increase the distance, you're going to decrease the amount of energy between them, right? Because if you have 2 ions that are close together, that's going to be just like if you have 2 magnets that are close together, that's going to create more energy involved, right? It would take more energy to break them apart than if they were further apart from one another. So that's why radius is inversely proportional to the lattice energy. Or sorry, directly. Inversely. Yeah, radius goes up, energy goes down. So inversely. And then it's also based on the charge. So Q1 and Q2 are simply measured +1, +2, depending on the ionic charge. So if you have ions of large charge, meaning +2, -2, that's going to create more of a lattice energy because they're stronger. It's kind of like having 2 stronger magnets next to each other compared to 2 weaker ones. Which one is going to take more energy to break apart? The stronger ones. So we can measure and calculate the lattice energy of a crystal structure of an ionic compound based on its charges, its radius, and it also involves a constant. This is the constant. So here is the lattice energy formula. So energy, it's a potential energy also, because keep in mind, nothing's moving. So this is just the energy of, is there a definition for lattice energy here? There should be. Yeah, so basically I'm going to write it down here. So that's the equation for lattice energy right here. And here is the definition. Lattice energy is energy released when ionic bonds are formed. So energy is released when these ionic bonds are formed. And the amount of that energy, and keep in mind, released, that means is this process exothermic or endothermic? Released always means negative, right? So exothermic. Yeah. So yeah, released. I'll underline that. Okay. So here's the formula, and here's this weird like E0, they call it. And it is a constant, and it represents, and it kind of is just, there's a whole derivation. It's a physics constant, and they use this in the formula. And Yeah. So yeah, there's a formula. And if you need to use this, you'll be given this formula on the exam, and you'll be given every variable you need to solve for it, basically. So, lattice energies, we know they're exothermic, they're always negative, and they are generally large. I mean, large is a relative term, so some of them are smaller than others, but it's important to look at a couple things. The first is the formula. So, you notice how this formula is the standard formula for the formation of ionic compounds. It's standard because it's per mole. It's per 1 mole. And if you have it per 1 mole, you notice that why is there a half here? Like, didn't he teach us you can't do that? I mean, you can, because if this represents molecules, you can't. But if it represents moles, which it does, because the enthalpy of formation or the lattice energy is kilojoules per mole, in this case, you can represent 1/2 of a mole of chlorine gas. And this equation wouldn't work any other way because we want to express the formation of NaCl by mole. So these are the way the standard equations work. We're going to be breaking down this equation in the next couple slides and talking about the energetics, meaning the different processes that occur in order for you to calculate the lattice energy and of the formation of NaCl, for example. So it's called the Born-Haber cycle, and we'll be talking about that not in super detail, but we'll just go over what it means and then an example of it. And it may be one example on the test, but it's not too crucial. Yeah. Okay. So something else that we're going to talk about later that is important. So if you look at the melting points of some common ionic compounds, right? Melting point. Now, do you notice a trend? So melting point means the energy, really not like temperature, obviously, but it means the energy required to melt it. So if you have stronger bonds, then it would require more energy to disrupt those bonds and to melt the compound. So if you have a higher lattice energy, that would mean you have a higher melting point, because in order to disrupt the intermolecular interactions, you would need a lot of energy to kind of make a solid into a liquid, right? So does anybody know, or can anybody see any trend here in terms of what type of ions we're dealing with, what happens to the melting point, etc.? There's two trends, but one of them might be apparent, the other one might not be. Anybody?
Like things closer to becoming a noble gas have a lower melting point.
Closer to becoming a noble. Okay, so you mean like the fluorine, chlorine, bromine, and these chlorine ions have a lower melting point than the other ones? Is that what you mean? That's close, but you're on the right track. So yes, on the right track. So what about those ions, the ones that are closer to becoming a noble gas, meaning the halogens, the fluorine, chlorine, bromine, chlorine that are over here?
Their lattice energy is lower.
Their lattice energy is lower, yes, because they have lower melting points. But what about their charge?
Their charge is only -1.
Good. It's only -1, meaning they're with a +1. Good job, Gabriel. So they're a +1, +1, -1. What about the other ones?
Plus.
Let's say the highest one. The highest ones.
Well, Mg's a +2.
Good. So they're +2, -2. And look how much higher the lattice energy or the melting point would be if you have a +2, -2 compared to a +1, -1. It's a lot higher. So that represents the amount of charge I'll tell you right now, there's two factors, but the amount of charge, whether it's +1, +2, +3, is the biggest determinant of lattice energy. So good job. Now, we'll continue. So yeah, and if you have a mixture, let's say calcium fluoride, where calcium is +2, fluorine is -1, it's kind of in the middle. So it's higher, it's a stronger interaction than a 1 and a 1, but it's not as strong of an interaction as a 2 and a 2. So it's kind of in the middle. But yeah, so that's a good observation. And there's another factor that determines the lattice energy and the melting point. And other than the charge, the other is the size. So if you have smaller ions, they're going to have a stronger interaction because they're going to be physically closer together. Their nuclei are going to be closer together. If you have larger ions, they're going to be further apart. So barium and oxygen. So these are all oxides: magnesium, calcium, and barium. Barium is lower on the periodic table. Magnesium is higher. The lower you go on the periodic table, the more electron energy levels you're adding to the atom. Therefore, the bigger the atom. So barium is a really big atom with oxygen. Therefore, the melting point's pretty low compared to magnesium. That's almost 1,000 degrees higher. And magnesium is a lot smaller than barium because it's higher up on the periodic table. So you see how size directly impacts lattice energy, and it also impacts melting point. And you can kind of see that for the other ones too. Sodium fluoride is very tight because sodium is very small, fluorine is very small, and it has a high melting point, high lattice energy compared to the other ones. But you see how that trait of size doesn't take as much precedence as the strength of the interaction, meaning +1 or +2. You take the smallest +1 -1, it's it's 3 times less than, or it's even twice as less as the biggest +2 -2. So the charge is more important. Okay, enough about that. So let's talk more about the Born-Haber cycle, right? So here's the equation for Born-Haber cycle for the lattice energy of formation of a salt. And you're all like, what the hell is this? Do I need to memorize this? Well, kind of actually, but it's a lot easier than this says. Now, in our standard equations, I guess we'll just go to here. Yeah, well, I'll explain this. Here's the Born-Haber cycle. Don't freak out yet. So you have the standard equation. Let's look at the standard equation first, which is your metal in a solid form plus 1/2 of the moles of your chlorine or your halogen or whatever or your nonmetal in a gas is going to create 1 mole of your salt. Now, in order to decode or to determine the heat of formation, the energy of formation, which is right here, of 1 mole of this, you need to understand the steps in kind of like converting the energy associated with the conversion of each atom involved, of each molecule or atom involved. So what that means. Now, something in chemistry that maybe I talked about mass spec the first lecture in class, but in order to ionize, either give an electron or take one away, you need to have your atoms in gaseous form. That is the easiest way for them to gain or lose electrons in terms of energy. So the first thing we would need to do, and you need to be on an atom basis. So you can't have a molecule, or you can ionize a molecule, but it's a lot easier to have it in a single atom. So what we would need to do is just understand, we're basically adding all these processes together. So the energy of sublimation of the metal, take that energy. So we need to make each of the metals into a monatomic, or each of the reactants into a monatomic gas. What does that mean? 1 atom and a gas. So the metal, we sublimate it, turn it into a gas. There is a certain energy associated with that. We add that energy here. Next, we're taking that gas and we are ionizing it. So that means we are giving it we're taking away an electron, right? Metals like to be ionized. They like to lose electrons. There is an energy associated with that, which we learned last class called the ionization energy. So we add that. Then we'll take a break there. We'll talk about the nonmetal. The nonmetal is already in a gas form, so it could be ionized very quickly, but it's not monatomic, meaning it's Cl2 or X2, whatever it's going to be. We need to dissociate. There's an energy of dissociation between those 2 atoms of that nonmetal. An energy is associated with that. We add that energy. Then we need to give the atom an electron from the metal that was just ionized, which is called electron affinity. How much does the atom or does the element like an electron? So if it's fluorine, it'll be a lot of electron affinity. So we add, and usually electron affinities are negative, so we'd add that number here. So, and then it would go, so we would basically subtract that number, but add the negative. Then you add the electron affinity. So then at this point, you have your charged monatomic ions. And then you add those together and you add your lattice energy to get the energy of formation. And lattice energy will be given also. Or maybe you have everything except for one and you need to figure it out. Okay. Before we do an example, is there any questions? Because this could be difficult. So basically we're converting all the reactants to what we need, which are monatomic ions. And then we are adding the lattice energy, meaning the energy associated with them combining atom to atom. And then we add all those up, and it gives us the energy of formation. So the energy associated with every part of the formation of this random salt. Any questions? No? Okay. All right. So practice. Given the information below, determine the lattice energy of MgCl2. Okay. So, and you're being given all this information. So it's important that you understand what's going on here. So let's write the equation first. Oh, here it is. Here's the equation. So, and I know this one's the equations because that's the standard. Oh, wait, that's not the equation. Sorry. That's the, it's almost the equation. Actually, no, it is the equation because it's 1 mole. So it's MgCl2. Okay. So that is the equation. So I'm going to put it in bold. So does everybody understand how this is our main equation? Oh, I don't know why that happened again. Copied it. It's our main equation because it's the energy of formation of 1 mole of our salt. In the examples we saw before, it says 1/2, right? This is if it's a +1 -1, like here. But in this case, we have a +2 -1. So it's going to be Mg plus Cl2 equals MgCl2. All right, cool. So that is our energy of formation. So now, to decode this, what we need to do, and here's what I'm doing. Take this. I'll take this equation. I'm going to put it on the next page so we can do it together. Oh, no. What did I just do? There we go. New slide. Okay. Make it bigger. All right. Cool. So now, what we're going to do, you get the pen. Okay. So we need to convert the reactants to what we need. So magnesium needs to become a gas. So I'll write sub. So we also have the energy of formation. So I'm going to write the equation on the bottom as we decode it. So the energy of formation equals -643, nope, 641.3, which is going to equal everything combined together, all these different steps. So sublimations first. So I'll put Mg sub plus. Once we get the Mg sublimated, it turns into Mg gas. Oh, there was a question. My computer's being really slow right now. I need to restart it. Okay, no problem, Chris. All right, so Mg gas. Then we are converting this Mg gas into an ion. So we need the ionization energy, IE. And I'm going to put IE1 because in order to ionize magnesium to its standard magnesium ion of +2, there is 2 steps. The first one is ionization to magnesium 1, magnesium +1. The second one is the ionization to from magnesium +1 to magnesium +2. So remember, there's multiple ionization energies for each atom, for each element. So yeah, so we need to add both of those together, one electron at a time. So that's done there. So now we're going to add IE1 plus IE2 and plus whatever we have left. Then chlorine. So chlorine we need to dissociate. I'll put dis. That makes it Cl gas. So we add dis. Then we have to do electron affinity, because chlorine, they create an anion. So chlorine. So Cl minus. It gains a electron. Okay, cool. So now we're done with that. So we need to add Ea. But there's one more thing. Chlorine, there happens to be 2 chlorines. So this happens twice. Dissociation happens once, but electron affinity happens twice, because you need to gain an electron for each of the chlorines. So this needs to be 2. And then there's going to be plus your lattice energy, because remember you had that arrow here that goes like that. And it's going to be lattice energy. That's going to equal your HF. So yeah, does that make sense? So now what you do is you take these numbers for the different steps, and then you would add them accordingly. All right, so they take double the dissociation. I don't need to do that. I guess you do. Yeah, okay. So they could do, yeah, okay. So I guess you have to do double the dissociation also. So 2 dissociation. And that's your equation, because you have 2 chlorine ions. So you do double, even though it makes sense that, oh, isn't there just 1 dissociation because you have chlorine 1 and chlorine 2? And that's not how it works for some reason. I don't really know why, but that's not how it works. So you need 2 dissociations. So you're doubling those. Okay, so once you solve that, you would get your answer, and it would be that. And that is your lattice energy for magnesium chloride. Okay, any questions?
No, it's not that bad.
Yeah, right? You just got to go through stepwise. Also, like I said, it's not a big thing of this chapter, just there may be one of them. So yeah, kind of like study this last. We'll put it that way. So if you have time, study it. Don't freak out over it, and don't spend most of your time on it. Okay, so now we're going to move on to the trends in ions. So I talked about this already. So larger ions mean weaker attraction, which means smaller lattice energy, smaller melting point. So large ions are not favorable for lattice energies, because we talked about the distance, they're further away. Now, it's important for you to remember, this is another reason why it's important for you to remember atomic radii, because this comes into play. You're going to have to know, just based on looking at different ionic compounds, which ones are larger and which ones are smaller. So it's important for you to understand the size. And here's some examples of that. These are all chlorides. And as you increase the size of the cation, you see the lattice energy decreases. Decreasing meaning the absolute value decreases. You see how they get further apart. So this is another thing like electron affinity, where it's exothermic. And when I say decreasing, I mean the magnitude, the absolute value decreases. So lithium chloride releases 834 kilojoules per mole when it's formed. Cesium chloride only releases 657. So therefore, cesium chloride is smaller. So it's based on magnitude. Then you have based on charge, and we know charge is the most important thing. So the larger the charge means the stronger the attraction, and the larger the lattice energy. So of the 2 factors, charge is generally more important, because it's I don't know, I mean, it just is. So I'll tell you why. Because the sizes are not really that far off. They're off by picometers. They're off by 10, 20, 30 picometers. Meanwhile, the the charges are magnitudes different. So here's an example of two ions that are relatively the same charge, same distance. So you have 231 picometers, 239 picometers, about the same. Meanwhile, calcium oxide is a +2 -2, and it is over 3 times the amount of lattice energy that sodium fluoride does. So that's a good example of that. Okay, so whoops, there's the answer. Ta-da. Wait, I want to, here. Don't look at the screen. Okay. Now you can do it. So I'll give you guys a minute or two. Order the following ionic compounds in order of increasing magnitude of lattice energy. So that means smallest to greatest. And then melting point. Melting point is directly proportional to lattice energy. So small melting point, small lattice energy. So I'll give you until 39 to do that. So 9:39. So it's 9:37 now. And I'll work through it with you. Gibril, good job. Okay, since Gibril said the answer, we will go over the answer.
Professor,
Yes.
it's pronounced more like Jabril.
Oh, it's Jabral?
Yeah.
Oh, I'm sorry. I thought I... Oh,
No, it's fine.
okay. I'm sorry.
So,
Yeah, thank you for letting me know. Jabral, got it. Okay. All right, good job, Jabral. So let's do this. Okay. So lowest lattice energy, right? The lowest energy is going to be the ones that are further apart and a +1 -1. And first, let's look at all the +1 -1s, which we have KBr, KCl. Sorry, favor. I'm going to mute the microphone. Your microphone. Sorry. Okay. Okay. So KBr, KCl. So out of these, which one is larger? They're both potassium. So bromine is lower, so therefore it's a little bit larger. So that means it's going to be slightly less lattice energy than something that's closer, which is KCl. So we know it's going to be KBr, then KCl. Now we have to look at the +2 -2s. Calcium oxide versus strontium oxide. Calcium oxide has calcium, and then strontium has strontium. So strontium is lower on the table. Therefore, it's going to be further apart. There's going to be a larger distance. So strontium oxide is going to be less of a lattice energy than calcium oxide. So Jabral, you are correct. Good job. Extra credit. Just kidding, but nice. Any questions? No? All right, cool. All right, so now we're going to learn about Lewis structure. So for covalent bonding, Lewis structure is really important. It can tell you the amount of bonding electrons, non-bonding electrons, the formal charge of compounds, the formal charge of each atom. It can tell you a lot. So the way it's represented, which we kind of saw already for ionics, is you have this thing called the octet rule we'll talk about. Then you have bonding pairs of electrons and lone pairs of electrons. So AKA non-bonding pairs. So they're lone pairs. Now, in a Lewis structure, so here's what one would look like. So this is calcium, not calcium, bleh, carbon dioxide. And here is one way to represent the Lewis structure. Another way you can represent it is this. That's another perfectly acceptable way to represent it. Now, you have a lot going on here, and we'll talk about how it's bonded in a second. And it's very easy to understand. But you have lone pairs of electrons that are just the dots, and most of the time they're always in pairs. Very rarely you'll see one by itself, and if you do, it's called a radical. Those are very unstable. So that's why, quick little aside, antioxidants. Antioxidants, what they do is they bind to oxygen radicals, which are just oxygen with one lone electron, like that. That's an oxygen radical. Those are very bad for the body. They actually interact with our DNA, with our DNA side chains and our amino acids, and they could actually damage our DNA and lead to mutations and lead to cancer. So that's why, yeah, antioxidants are really good for reducing your risk of heart disease, cancer, and all that stuff, because they eliminate or bind to these oxygen radicals and make sure they don't bind to your DNA or to other important structures in your cells. So oxygen radicals are bad. And a good question is, how do you get oxygen radicals? Well, generally by doing unhealthy behavior, such as smoking, drinking, unfortunately drinking, yeah, but doing just eating like a lot of fast food, generally considered unhealthy behavior, is not good for oxygen radicals, and they tend to increase oxygen radicals. So anyway, the oxygens we're going to be dealing with are not radicals. They have lone pairs of electrons, not lone single electrons. So here's what calcium or carbon dioxide looks like in a Lewis structure. Each one of these is acceptable. Now, you have lone pairs of electrons, and also you have these bonds. So you can see by comparing both of these structures that you can tell that each bond represents the sharing of two electrons. That's exactly right. So you can have your double bonds here, and then there are single bonds where it's just sharing of two electrons or one pair, and then you have triple bonds where it's sharing of 3 pairs of electrons, and those are the strongest ones. So that's generally how a Lewis structure looks. Now, I talked about this already, basically saying, I just want to get to the examples, but we can predict their formula, we can predict their 3-dimensional structure, their stability, all that stuff. So Lewis structure is a very good thing to do. So yeah, covalent compounds have low melting points and low boiling points, but that varies because the strength of them, they're strong, whatever. Okay, so here is important things. So we're going to talk about this, and then we're going to do some practice. So here's important things to keep in mind when we're talking about Lewis structures. So bonds, and there's a you don't have to just cold remember all of this. It makes sense based on the periodic table. So carbon always has 4 bonds. Very, very important. If you're in organic chemistry and you write carbon with 5 bonds, you're going to be laughed at because it always has 4 bonds. Sometimes it might have 3 and is a weird charge somewhere, but in our level of chemistry, even organic chemistry 1 and 2, carbon is going to have 4 bonds and no lone pairs. Nitrogen would have 3 bonds and 1 lone pair. That's almost always a rule. Oxygen will have 2 bonds and 2 lone pairs. This is for it to be completely satisfied. If sometimes oxygen might have 3 bonds, but in that case, it's not very stable. It has what we call a formal charge. And we'll talk about that later on. But generally, oxygen, the rule is for it to have 2 bonds. And it will look like this on the bottom. So you'll have 2 lone pairs and 2 bonds. Hydrogen and halogens, 1 bond. But for the halogens, like you see fluorine over on the right side, fluorine and the halogens will have 6 lone electrons, 3 lone pairs, plus 1 bond. Hydrogen will only have 1 bond. So hydrogen will look like this. Like that. And it'll have no lone pairs. Beryllium is a weird one. Beryllium and boron do not follow the octet rule. So beryllium just likes to have 2 bonds like this with no lone pairs. Boron, 3 bonds, no lone pairs. And then the group behavior is similar. So oxygen compared to sulfur most of the time. Sulfur can also take 6 bonds and 2. Sometimes it could even take 4, but mostly it's 2 and 6. Phosphorus, 3 and 5, mostly 3. It kind of acts like nitrogen. Okay. So some of you are thinking, what the hell? There are so many rules. What's going on? Really take it in terms of the problem you're trying to solve. Know the basic ones. Carbon's 4, nitrogen 3, oxygen 2. And it makes sense on the periodic table because in order for carbon to take in 4 bonds, that means it has to gain 4 electrons, meaning to be shared in its shell. Carbon has 4 electrons to begin with. It's in 4a, right? So it gains 4 electrons, meaning it gains 4 bonds, and then it has 8 electrons, so it's happy. Nitrogen has 5 electrons, therefore it needs to gain 3, so it's happy. Oxygen has 6 electrons, needs to gain 2, and then it's happy. Halogens need to gain 1, and so does hydrogen. They gain 1 electron in a covalent bond, so they have 1 bond. Boron, 3, and those are just exceptions. Sulfur needs to gain 2 electrons, so 2 bonds most of the time. Phosphorus, same as nitrogen, 3 bonds. But there are exceptions. So is there any question? I know I kind of just like rattled through those, but is there any questions on anything I said about the number of bonds? It's weird because it does change, but once we do examples, it should make more sense because it depends on the example. No? Okay. If not, then let's do an example. So I'll do the first one. I'll do the first 2. I'll do the first one and the third one. And then you guys can do the second and the fourth one. All right. So NH3. The first thing you have to keep in mind is how the hell am I going to write this? What is that like? What do I start with? In other words, which atom do I put in the middle? Which ones do I put on the outside? And it would be a stupid thing for me to say, well, it just kind of makes sense. Like, you just know. I mean, if you're exposed to this for a while, yeah, you kind of just know. But it is, normally, there are rules for it. If you see carbon, 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 and carbon, it's always carbon. Carbon is always in the middle. If you see hydrogen, 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 hydrogen is always not in the middle. Another thing is, let's say you have something that doesn't have either of those. Let's say NCl3. It's usually the atom that contains, it's usually the element that has the least amount of atoms. So nitrogen has the least amount in this case and also in this case. Therefore, it's the central atom. So, yeah. If it's tied, then there is no middle atom. So then it's kind of just symmetrical. But you can kind of deduce that information, which one's in the middle, based on if it's carbon, if it's hydrogen, and if it has more atoms or less atoms than another element in the compound. If you see halogens, generally they're not in the middle, but there are exceptions to that as well. There's elements that are like xenon tetrafluoride, which is a noble gas that's in the middle. It takes 4 covalent bonds. It's weird. It kind of violates all the rules. It violates the octet rule, but that exists, and it's kind of stable. So that's weird. So there are exceptions to these, which we'll talk about, but not right now. So we'll do NH3 first. So we know nitrogen's in the middle. Next thing you do is you just set them up. You set up all of your atoms. Then the next step is we write in the amount of dots that are the valence electron number for each atom. So hydrogen is 1, hydrogen's 1, hydrogen's 1, nitrogen is 1, 2, 3, 4, 5, based on the group on the periodic table. Oh, what just happened? There we go. Okay. The next step is we write our bonds. So get in the perspective of the atoms. Nitrogen, I need 8 to reach our octet rule. I have 1, 2, 3, 4, 5. I need 3 more. Oh, look, 1, 2, 3. I could do that. Hydrogen, the perspective of hydrogen is like, I need 1 more electron and I'm good. All right, I will share with you. I'll share with you and you. Ta-da, that's it. That's the Lewis structure for ammonia. Because if you look at it at the end, nitrogen has 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. It's happy. Hydrogen is also happy. Hydrogen only has a maximum of 2 electrons. Very important. Hydrogen has max of 2. Very important. Okay. So, and also you see these lone pairs. So sometimes they might be there, sometimes they may not. Okay. Any questions on that for ammonia? Okay, we'll do this one now. So H2CO. We know carbon's in the middle. We know hydrogen is not in the middle. So oxygen must be bound to the carbon. But there are some cases where you may think this. That's a totally valid configuration, but we'll see why one of them makes sense and one of them doesn't once you actually do the work. All right, so now we're going to draw our electrons. Hydrogen has 1, hydrogen has 1, carbon has 4, 1, 2, 3, 4. And it doesn't really matter where you write the dots, as long as you clean it up at the end. I'm writing them in the perfect configuration because I know what I'm doing, but if you're just practicing, write the dots wherever you want. Sometimes you see carbon with 1 on each side. So it doesn't matter, as long as you fix it up at the end. And oxygen has 1, 2, 3, 4, 5, 6. And then we'll do the same here. 1, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 1. Okay. So now let's do the wrong one first. This one's wrong, but let's do it first. So oxygen needs 2. All right. 1, 2. Carbon needs 4 bonds. 1. Then you get stuck. Because look, oxygen is already satisfied. If you like, okay, carbon needs 4 bonds, I guess I'm doing this, then oxygen will now have 4 bonds as well. That's not good. That's really unstable. That's bad. So that's why that's not the answer. There's only one way to make it work. So let's look at this example. Carbon to hydrogen, that makes hydrogen happy. Carbon needs 2 more bonds. 1. Oh, this guy was missing. 2. Ta-da! Everybody's happy. Yeah. Okay, cool. So any questions on that? Okay, so I'll give you a couple minutes to do the second one and the fourth one by yourself. The second one should be easy. Fourth one, you might have to think a little. And it's 9:55. I'll give you till 9:58. And then we'll go over them. I'll start going over the first one. So CH4, this is called methane, which we've used as examples many times. So for CH4, you know, carbon's in the middle, and you're going to have 4 hydrogens on the outside. And then each hydrogen will have 1, carbon will have 4, and it's a simple single bond to each of the hydrogens. So that's a very easy one to do. So now let's do HCN. So we know carbon's in the middle. We use different color. We use black. All right. So now we have our electrons. We have 4 around carbon, 1 on hydrogen, 1, 2, 3, whatever. You can put them however you want. So I'll do them randomly like that. So let's see how this works. We know that carbon needs 4 bonds. So let's just make one with hydrogen. We know that's going to be a thing. So now hydrogen's happy. Now nitrogen. Nitrogen needs 3 more. So 1, 2, 3, 4, 5. It needs 3 more electrons shared with it to have its octet rule. So does carbon. It needs 3 more. So you make a triple bond. 1, 2, 3. So everybody is happy. If you can count them up, carbon has 4 bonds, 8 electrons. Nitrogen has 3 bonds, 2 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. And then if you clean it up, it would look like this. 1, 2, 3, like that. That's hydrocyanic acid. Okay. Any questions on those, on how to do these Lewis structures? There are ones that are weird, that don't follow the general scheme of Lewis structures, that violate the octet rule, such as, we'll do 2 examples of that. SF6 is a very common one, and we'll do the xenon tetrafluoride like I mentioned. No, that's 2. Xenon tetrafluoride. 4. So let's do SF6. Now, even though if you don't really know what's in the middle, it's going to be sulfur because it's just like, and you can tell it's probably going to be sulfur. Fluorine has less of them. You know fluorine likes to take 1 bond. So 1, 2, 3, 4, 5, 6. Sulfur has 6 valence electrons. 1, 2, 3, 4, 5, 6. Fluorine, each one of them has 7. So I'll just put the 1 here. Assume it has 6 other ones. And then you do single bonds like that. Like that. So it's just going to look like this. And then each fluorine will have 6 more valence electrons on it. Now, if you're doing a Lewis structure and you're not sure if it's right, what you can do is you can count up all the valence electrons, meaning the bonded ones and the non-bonded ones, to check your work. So for fluorine, you do 1, 2, 3, 4, 5, 6, 7, 8 for the bond, and then you would add them up accordingly. So, and you would see if that's right. That's one way to check it. Okay, so now for xenon tetrafluoride, xenon's in the middle. And this kind of goes against all the rules, I know, but these things exist. Xenon is a noble gas. It has 8 valence electrons. So how's it going to bond? Well, it does. Why don't I write Fe? So you have your fluorines. Each one of them is going to have 7. But I'll just write the 1 that it bonds with. And it's going to be just single bonds with the fluorines like that. And then you'll have 2 lone pair electrons, 2 lone pairs of electrons. on the xenon, on the central atom. Okay, does that make sense? Those are two weird ones but they always occur. I mean, you might see those. Any questions? Now, some of you may be thinking, why is this the case? Why are we allowed to just break the octet rule, and why is it stable? And that's a good question. And the answer has to do with what we're going to learn next, which is electronegativity and formal charge. So the idea basically is, before we get into it, the idea is we want to satisfy the atoms, or we want to satisfy the elements that have the least, that are the least reactive. Or no, the most reactive, sorry. We want to satisfy the most reactive elements. So if you have a, I don't know, I play baseball. So if you have like our team's kind of nuts, but let's say like you have one kid that likes to start fights with the other team, right? And everyone else is pretty cool. So you want to make him happy so he doesn't start fights with the other team, because you don't want to have fights with the other team. Same concept. Fluorine is the crazy guy that likes to start fights. You want to keep fluorine happy, meaning have one bond, have all 8 valence electrons happy, because you don't want fluorine to start problems and to start reactivity issues with everybody else nearby. So if fluorine's good, you're good. Something like a noble gas is very noble. They're not going to react with anything. So if you have to force them to be not happy, they'll deal with it, at least more than fluorine. So like if, I don't know, someone strikes, you don't want fluorine to strike out 3 times to go crazy. You want him to be happy. But the noble gas, he's just like, oh, I'm just here to have fun, whatever, which is totally not how I see it. I'm more like fluorine. But yeah, you get the point. Okay, so the way we determine this reactivity and how to satisfy the elements in a Lewis structure is by this thing called formal charge. So a formal charge is a measure of how much something fills the octet, how many more or how many less electrons it needs to fill up its octet. Sometimes the formal charge may not be 0. If it's 0, that's great. In all of these Lewis structures that we did first, these first 4, the formal charge for every atom was 0. And then they're perfectly stable molecules and they're good to go. In these, it's a little bit different. And we'll talk about how to calculate formal charge now. So it basically is a measure of how stable something is. A formal charge of 0 is great. A net formal charge of 0 means it's a stable molecule. So you can determine and calculate the formal charge of each atom in the covalent compound. If the entire molecule adds up to 0, that's great. If each atom is 0 and the molecule adds up to 0, which that's the only case, then that's perfectly stable as well. Sometimes the molecule might have a formal charge on its own, which that's when you get a little bit of instability, or sometimes you get ions that like to form ionic compounds with other things. So there's a way to calculate it. The way that they say in the book to calculate it is you take the valence electrons of the atom minus the non-bonding electrons minus 1/2 of the bonding electrons. Now, me personally, I hate that description. So there's an easier way to think of it. So the formal charge is also equal to the valence electrons minus the electron, well, minus the electron, what was the way I said it? Minus the amount of stuff. There we go. Amount of things, minus things attached to atom. You see how this would not be in a textbook because things attached to an atom. Like, what does that mean? I'll explain in a second. So I'll take this definition and I will copy it to the next slide. So here is an example of, well, it's not really practice. We kind of just did it. The only answers are here, but we'll talk about it. the formal charges of different atoms in different covalent compounds. So CO2, we've seen the Lewis structure for CO2, and we see that they're all 0. But let's calculate them one by one. Whatever. All right, so let's calculate them. So using my definition, valence electrons of oxygen is 6 minus the things attached to the atom. What I mean by things is literally things. A bond is a thing. So 1, 2, an electron is also a thing. 3, 4, 5, 6. 6 minus 6, 0. So thing equals electron bond. I could have just said the valence electrons minus the electrons and bonds. I like that better. Minus lone electrons and bonds. Okay, that's better. All right, so does that make sense? Is there any questions on that? We'll go through all of them. So carbon, valence electrons of carbon is 4. Electrons and bonds, 1, 2, 3, 4. 4 minus 4, 0. CO2 is very stable. Let's look at this one that's not so stable. Selenium, oxygen, whatever that's called. Selenium, I don't even know what that's called. But whatever it is. So fluorine, we'll do fluorine first. We'll do selenium first. So selenium, where is selenium on the periodic table? I think it is below oxygen. Is it? Double check. Let's see, where is selenium? Selenium is below sulfur, yeah, so it's below oxygen. All right, so selenium is going to have 6 valence electrons also. So 6 minus the amount of electrons and bonds. 1, 2, 3, 4, 5. 6 minus 5 plus 1. That's not good, but let's see what happens with the rest of the molecule. Fluorine. Each fluorine is the same, so we can just calculate the formal charge of one fluorine, and it is 7 minus 1, 2, 3, 4, 5, 6, 7. 7 minus 7, 0. Oxygen. So this one is also 0. Oxygen, it says -1, but we'll calculate why. 6 minus 1, 2, 3, 4, 5, 6, 7. -1. Add all these up, you get -1 plus 1, which is 0, 0 and 0. Selenium fluoride or selenium oxygen difluoride, whatever it is a 0 formal charge total, meaning it's pretty stable. Does that make sense? Okay. Hopefully that means yes. We'll do one more. We'll do SO3 minus 2, and then we'll move on. So this one's not that stable, and this is the sulfite ion, SO3 minus 2. And the reason why it's -2 is because of formal charges. So now it should have clicked in your head maybe that, oh crap, the ions, the polyatomic ions that we learned before, I told you they were just covalent compounds that had a charge, but here's why they have that charge. Because each of the atoms has a formal charge. And that explains why they're not stable. Because with a net formal charge, it's not stable. It needs to interact with something. In sulfite's case, it wants to interact with a +2, or like a calcium or something, or a magnesium, something that will make it happy. So let's go through this and see how their formal charges are -1 and +1. So for oxygen, 6 minus 1, 2, 3, 4, 5, 6, 7. That's a -1. For sulfur, 6 minus 1, 2, 3, 4, 5, +1. Add all those up. These will cancel. Then you have a net formal charge of -2. So then you have sulfite -2. Okay. Is there any questions on that? And I know I went through how to calculate the formal charge quickly in these examples, but is there any questions on how you do it? You basically do the valence electron number of the atom minus the amount of electrons and bonds that are connected to it. So you just basically count everything. You count everything. So 1, 2, 3, 4, 5, 6, 7 for this oxygen. Any questions on that? All right. If not, we will keep going. So the reason why we're talking about formal charge is because we want to minimize the formal charge to become stable. So the best structure is that a structure that keeps the formal charges to a minimum level. 0 is the ultimate goal, but sometimes you can't do that. So the correct structure, the most stable one, has the lowest formal charge of each atom and of the entire thing. So what I mean by that is even if the formal charge of an entire thing is 0, it would be weird if you had a formal charge of oxygen +4 or -4. That's incredibly unstable. You want to keep formal charges of atoms around +1, -1, +2, -2 at most. Never higher than that. Otherwise, it's very unstable. So you want to minimize all the formal charges. So let's look at these structures. This is SO3 and this is SO3. Let's see which one has, we saw the other SO3 before. So SO3 -2, in this structure, you had a -2 formal charge total. So we know for this one, the formal charge is -2. Let's calculate for this one. An oxygen with 2 bonds has a formal charge of 0. Sulfur is going to be 6 minus 1, 2, 3, 4, 5, 6. That's 0. This oxygen is going to be 6 minus 1, 2, 3, 4, 5, 6, 7. -1. This one's also going to be -1. So you have two options here, right? They both give you the same net formal charge of -2. But one of these is more stable than the other. Does anybody know which one? So in this case, sulfur has a formal charge of +1. There's a -1. Here's a minus. Actually, wait. Oh, yes. Okay, yeah. Does anybody know which one's more stable? Anybody want to take a guess? Either A or B. A, this is B. They have the same net formal charge, but individual atoms, it's different.
A is more stable.
So actually B is more stable. And the reason why is because you want to make, in making a stable Lewis structure, you want to make the most amount of atoms stable with a formal charge low as possible, meaning 0. In this case, you have sulfur and oxygen have 0 formal charge. That's good. And these two just have -2. Here you have a +1 and a -1. Everything has a formal charge here. So that's not as stable as this one. So you want to minimize the formal charges of all the atoms. So another way of describing it is when we talk about electronegativity, which is going to be next, we want to minimize the formal charge on electronegative atoms. Oxygen tends to be a very, well, not tends, is a very electronegative atom. We don't want to have formal charges on electronegative atoms. We would prefer not to. So the fact that this oxygen is 0, meanwhile all 3 oxygens here are -1, means this structure is going to be a little bit more stable. So good guess. Thank you for participating, because no one else seems to be participating, but it is this one. So, okay, good thing you know that now. All right, so then resonance. We'll talk about resonance real quickly. Basically, all of these different bonds are interchangeable. So why are we putting a double bond here in the sulfite structure when we could put it to this oxygen or to this one? And the answer is there is no difference, meaning these bonds actually rotate between double bonds and single bonds because there's no preference. There's no preference between the sulfur making a double bond with each of these oxygens at all. It's just random because there's no preference. So resonance, they go crazy on resonance, but the only thing you need to know about that is the double bonds move. That's it. So here is a rule for resonance, I guess, but it's really just they need to be exactly the same compounds, right? So the connectivity needs to be the same. The number of electrons need to be the same. They basically all need to be the same, but only thing that's moving is the bonds. So we can go crazy on that, but it's the same thing. It's just you're moving the bonds over, and it's going to be the same exact thing. If you rotate the top structure, it's the same thing as the. If you take a mirror image of the top structure, it's the same as the bottom. So, yeah. Okay, so don't really worry about drawing resonance structures. You just, if I asked you, draw a resonance structure of this one, of the top one, just move the double bond over here or over here and make this one. This is nitrate. There's 3 resonance structures of nitrate. The third one is this. Basically just moving the double bond where it isn't already. Yeah, like that. So that's it for that. Okay, so now we're going to talk about another important thing, which is bond polarity and electronegativity. So the reason why in these Lewis structures we want to keep oxygen happy, we want to keep oxygens happy, fluorines happy, halogens happy, even nitrogen happy, because they are very electronegative. So bond polarity talks about electronegativity, but what bond polarity is let's say you have, I think maybe I talked about, well, whatever, we'll talk about it again. So let's say you have hydrogen gas, right? There's 2 electrons in the hydrogen gas molecule, and they're in the only covalent bond. These electrons are shared equally because they're in the middle, and they're both hydrogens, and there's no reason for them to share unequal. This means the bond is non-polar. So this is non-polar, meaning the electronegativity between each of the atoms are the same, or they're the same atoms, in which case there's no unequal sharing of electrons. When you have a polar bond, that means the atoms are not the same, and they're actually very different in terms of electronegativity trend, which we'll learn about in a couple of slides, and they create an unequal sharing of electrons. An example of that would be HF. It's a weak acid, hydrofluoric acid, and it is very polar. The reason why it's polar is because fluorine is a lot more electronegative than hydrogen. Therefore, in the covalent bond, the electrons are a lot closer to fluorine. That gives fluorine a partial negative charge, and it gives hydrogen a partial positive charge because it has the absence of electrons, since all the electrons are closer to fluorine. So that is how polarity works. Now, yeah, we talked about that. So, yeah. Okay, let's continue. Now, electronegativity, and you could determine, based on the numbers in electronegativity, the polarity of a bond. It's measured. And there is also a trend. So it's important to know the trend, not really the measurements. If you need to know the measurements, they'll be given to you. So generally, electronegativity, here's trends, increases across the period from left to right, and it decreases down the group. And what electronegativity is, it's the measure of a pull of an atom has on bonding electrons. In other words, how much does an atom like electrons when it's in a bond? That's basically it. It's very similar to electron affinity, and it's the same exact trend as electron affinity. This is just saying electron affinity in a bond. That's all electronegativity is. So fluorine is the most electronegative, just like fluorine has the highest electron affinity. Francium is the least electronegative, just like how francium has the least electron affinity. It wants to get rid of electrons the most. Does that make sense? And then furthermore, if you have a molecule, you can determine the electronegativity or the polarity of the molecule by taking the difference in electronegativity of the atoms that are in the molecule. And then the larger the difference, the more polar the molecule is. So let's do some examples. Let's look at electronegativity, the trend. So you see how on the lower left, I don't know why they don't have France. They're missing the row, but the lower left has the lowest electronegativity. All the metals generally have low electronegativity, and that makes sense because they don't want to get rid of or they want to get rid of an electron. They don't want to gain an electron. Meanwhile, the non-metals have higher electronegativity, and then fluorine's the highest with 4. So don't really worry about the numbers too much, but you need to, if you're determining the difference in electronegativity, you need to know the numbers. But, I mean, they'll be given to you. You're not going to have to memorize all of these. So we talked about this molecule already, HF, which is a weak acid, and where fluorine has an electronegativity of 4, and hydrogen has it of 2.1. So the difference is going to be very large. The difference is going to be 1.9. So we'll learn about what the number actually means, but 1.9 is a huge difference in electronegativity. Even something like 0.5 is the cutoff. 0.5 would be considered to be a polar molecule if you have an electronegativity difference of 0.5. Here you have over triple that. Therefore, it is extremely electronegative. And that means you're going to have a very strong partial negative charge on the fluorine because the electrons are a lot closer to it. And you're going to have a partial positive charge on the hydrogen because the electrons are far away. So what this means, this little symbol, this is a lowercase delta. So lowercase delta represents partial charges. And it's just like ionic charges, where the polar molecule could exhibit partial positive and negative charges based on the distribution of electrons to one atom or the other. And if you put an electrode here, you'll see how they would rearrange. And if you put a minus end, they would all orient in where the hydrogens will be going towards the minus end. And then the fluorines will be going towards the positive end, like that. So they align along an electrical field. And something being polar is why it interacts with water. So remember how we talked about how non-electrolytes break up, or how non-electrolytes are dissolved in water, like sugar. So we talked about how sugar, it is engulfed. The partial positive and partial negative charges of sugar are engulfed by the partial positive and partial negative charges of water. And then that molecule is taken in by the water and dissociated from its sugar crystal into individual molecules. And then that's dissolved.
Yes.
Your
Yes, I'm
question?
in it. I'm in it.
Okay, I will mute whoever's talking. All right. So, yes, that's how electronegativity works. So it's basically assigning partial charges, and then you create a polar molecule if there is a difference in electronegativity greater than 0.5. So here's another representation of the scale. You see it increases to the top right. And you notice how the noble gases aren't included because they don't want electrons. They don't even want a bond. So they're not going to have really any reactivity. There are some weird exceptions like gold. Gold is 2.4, but don't really worry about that. Okay, so here are the numbers. So if a difference of electronegativity, if a difference of electronegativity is 0, then it's a pure covalent. So you're only going to have that for things like that are the same element. Even FF, right? FF is going to be both, each individual fluorine atoms are going to have a very high electronegativity. But when they're bound together, think of it as an electron tug-of-war. They're both really strong, but in the end, the rope's not going anywhere. It's going to be in the middle. So there we go. That's pure covalent. There's another weird case with pure covalent. So if you look at the trend, let's look at phosphorus and hydrogen. So the pH bond, phosphorus and hydrogen, you see how they're both 2.1? You might think, oh, that means they're nonpolar. Actually, that doesn't. And the reason why is because of their size. Phosphorus is so much bigger than hydrogen. There is an unequal sharing of electrons just based on size. Same thing would occur with if hydrogen made a bond with tellurium or with astenine. Yeah, astenine. So the same thing would happen is even though they're the same electronegativity, they wouldn't have a nonpolar characteristic. They would be considered to be polar because of the size differences. So the only case where you can have a true pure covalent compound is if you have the same atoms bound together. Okay, so then you have nonpolar covalent, which would be your pH bond or your hydrogen tellurium bond, whatever, is where you have electronegativity differences between 0.1 and 0.4. So you have a small difference. Anything from 0.5 to 1.9 would be polar covalent. So you saw 1.9 was the top for when we talk about fluorine and hydrogen, that would be 1.9. Technically, here's another technicality. If you had fluorine and boron, technically the difference there would be 2. And it would still be covalent. And it would still be polar covalent. That's why I don't like these two definitions. So technically, well, not technically, but if you have an electronegativity difference greater than 2, so it's huge, it's going to be ionic. Yeah, that makes sense because of your metals have a very low electronegativity. But for this class and for the future, I don't want you associating ionic bonds with electronegativity at all. That would confuse you. You know what ionic bonds are. We learned about it the second week of class, which means there's a metal and a non-metal. Every single one of these other cases, they're all covalent bonds, meaning they have a metal, or sorry, they have 2 non-metals, 2 or more non-metals in these cases. Ionic bonds don't look at electronegativity at all to determine if it's ionic. You already know if it's ionic based on the presence of a metal and a non-metal. So just remember that when we're talking about electronegativity. Okay, any questions on that? And here's an example of all of those different things. So you have a pure covalent, Cl, chlorine gas, HCl as a polar covalent, and then you have sodium chloride as an ionic. So what these electronegativity differences do is they create a dipole moment. In other words, the difference in potential energy, the difference in the charge, in the partial charges, creates a dipole moment, meaning the charge is more oriented towards one side. And in all these cases, it would be the fluorine side. So you can convert electronegativity into dipole moments, but just know they're different things, but they're very proportional to each other. Okay, we're basically almost done. The last thing we're going to cover, metallic bonds, there's not really much to know about it. It's just a sea of electrons, and they're all over the place. I kind of talked about it already. But the last thing we're actually going to cover is bond strength and bond length. So is there any questions on polarity, electronegativity? Because I feel like I've been going fast, but no one's said anything. So is there any questions on electronegativity or bond polarity? You can always look it up on YouTube later on this lecture if you want to hear me say it again. And you can slow down the video. That's an option too. Because I just roll with it. It's weird, like that's why I don't like online teaching, because I can't look at your faces. If I change my speed of teaching based on how you react to it. So if you're like, if someone has like a questioned look on their face, then I would slow down or reiterate what I just said. But I don't know what you're doing. Maybe some of you are sleeping or texting, or I don't know, but I guess I'm just rolling with it. So, yeah. Okay. So bond energies. Now, with covalent bond, and we kind of talked about that last class or the week before whenever we talked about energy, chapter 7, I think. But bond energies, there's an energy associated with every covalent bond also. And there's just there's some rules, right? And it's kind of like, oh, no duh, of course that makes sense. But if you have more bonds, it's more energy, meaning it's more energy to break them apart. So this is the energy required to put into the bond to break them apart. So for a triple bond, it's huge. It's 800, whatever, for a carbon-carbon triple bond. For a double bond, it's 600. For a single bond, it's 300. That's because you have more electrons being shared in between the atoms. Therefore, it creates more, you need more energy to break those bonds. Also, the shorter the covalent bond, the stronger the bond. And that kind of makes sense with lattice energy, with ionic bonds. With lattice energy, the closer the lattice atoms are together, the more lattice energy they have. So the closer the covalent bonds are together, the stronger energy they have, meaning the more energy needs to be put in for it to be broken. So that's the same approach, where these are all bromides, but when you put in a small atom like fluorine, it's a larger bond energy because they're closer together. But once you increase the size of that halogen, go from fluorine to chlorine to bromine, you see how there's less energy required to break the bond, less bond energy because of their size increases and the distance increases. And the bonds generally get weaker as you go down the column because of their size. So there's trends, triple bond is greater than double bond, greater than single bond. Also, the bond, oh yeah, so the bond energy, this should be, the bond energy, oh, I see what they're saying. So as you go from left to right, the bond energy decreases, but that's very slight though. Hold on. So where's it? Here we go. So if we want to compare, yeah, that's not true. That's why I looked at that. I mean, that's not true at all. I don't like this. What was that? I don't like this because that's not true. The bond energy decreases from left to right across a period. It depends on a lot of things. It depends on the size. It depends on the electronegativity difference of each of the atoms. So, okay, disregard this statement. But this is true. It increases as you go down the column. That's still not true. Wait. Oh, length. We're talking about length. Oh, my God. I freaked out. All right, we're talking about length. I'm sorry. I thought we were talking about strength still. All right, let's just do that again. Trends in bond length. All right, so bond length, meaning the distance between the atoms, or the length of the covalent bond. If you have more electrons being shared, such as a triple bond, the bond length is going to be shorter because it's stronger, because there's more of an attraction, there's more stuff going on, there's more of a bonding force. It's a stronger glue. Therefore, the length is going to be shorter. If you have going to the right across a period, you have smaller atoms. Therefore, the bond length will be smaller and the strength will be higher. So here's one thing that's important. Oh, here's the rule right here. So as bonds get longer, they get weaker. So strength is inversely proportional to length. A short bond is a strong bond. A long bond is a weaker bond for covalent. So in covalent bonds, we don't have the +1, -1, all these different charges. So we're basing it all on the amount of electrons being shared, such as a single, double, or triple bond, or the size of the atoms. So whether they're big or small. And then electronegativity is a small factor, but those are the main two. And then the bond length is going to increase as you go down the column. That makes sense because the atoms are getting bigger. So yeah. Okay. Any questions on that? I know I kind of messed up because I thought we were still talking about bond strength and I freaked out. But bond length is inversely proportional to bond strength. I'm glad I caught that. Okay. So here's an example. Bond lengths. You see how as you go down the halogen, go down to all of the halogens to iodine, you see how the bond length is increasing, and therefore the bond strength decreases. So then you have you can determine the bond energies of a reaction from knowing the table of bond energy. So here's a table, a standard table from your textbook of bond energies. And if you're required to do this under the exam, it will be given to you. So we'll do an example of this before we're done. And so we're almost done. So now here's how it works. So in a lot of different things in this class so far, we talked about products minus reactants when we're determining energy of formation and other things like that. But when we're talking about bond energies, it's a little bit different. The equation is the sum of the bonds broken minus the sum of the bonds formed. So where are the bonds broken? In the products or the reactants? So there the bonds broken are going to be in the reactants, right? Because they're all going to be disassembled. And they're going to be reassembled into the products. That's where the bonds are going to be formed. So products. And this is going to be reactants. So we're basically just doing that. So now using, is it the same question? Yeah, same question. All right. So now we are going to find the enthalpy of formation of this reaction, or the enthalpy of reaction, knowing the chart. Okay. So here's how we do this. We do the sum. So H equals sum of broken minus sum of formed. All right. So in this case, it might get a little bit difficult because you need to get every single bond, and you can't just say, oh, this is close enough to an oxygen-oxygen single bond, but they're different. They need to be specific. So the bonds broken, you're going to have 1, 2. So a hydrogen-hydrogen single bond, which is 436. So 436 plus an oxygen-oxygen double bond, which is 498. Then you're going to take that number and you're going to subtract the bonds formed. So the bonds formed, you have hydrogen-oxygen here. I'll put 1. You also have another hydrogen-oxygen over here. So it's going to be 2 times hydrogen-oxygen, which is 464. And then plus an oxygen-oxygen bond in the middle. So that's going to be the last bond. So oxygen-oxygen is 142. 142. And then if you add all those up, you get a number, of course, and that number is negative 136.3. So yeah. Cool. All right. Is there any questions on that or anything? Because we're done. That was pretty quick. It was only an hour and a half. So cool. Yeah. So I guess I'll end the recording now. So then I'll put it on YouTube either today or tomorrow. And